Now here I'm going to give you a very interesting problem, and that interesting problem has many applications in mathematics all over the place. But for stating that problem, I need some terminology. So I'm going to describe binary rooted trees. Before I describe what they are, let me give you an example. So rooted is, you need a node. I'm just going to call it the empty set. We are doing set theory after all. I should not use anything else. Then every node can have at most 2 children. That is the meaning of binary. And it's a tree. So there are no cycles. So once I bifurcate, then I will continue bifurcating and so on. So for example, this is a rooted tree. It is a binary rooted tree. The way I am going to label it is also very simple. It's based on the positioning on the page. So the left one will always be called 0, the right one will always be called 1. So what will be this node? 0, 0. This is 0, 0, 0, this is 0, 0, 1, this is 0, 1, this is 1, 0, this is 1, 1, this is 1, 0, 0, 1, 0, 1 and 1, 0, 0, 0. Okay, so what is a binary rooted tree now formally? So it is a T which is a subset of zero one star. Okay, what is 0, 1 star? Perhaps you are confused about that. It is defined to be union of 0, 1 to the power n, where n is less than omega. So basically 0, 1 star is the collection of all finite length strings of zeros and ones. Looking at the example, it should be clear, and it should satisfy something. Satisfying if sigma is a prefix of tau and tau is a node in T, then sigma is also a node in T. Okay, so now let us look at this. So this is a prefix relation, states that sigma is a prefix of tau. Okay, so for example, 0, 0 is a prefix of 0, 0, 1. Prefix means something which occurs in the beginning, and 1 is not a prefix of 0, 1, 0, 0. Obviously. So what we are saying here, that if tau is a node and sigma is a prefix, then sigma is in T. Sigma is also a node. Now here, because we are talking about trees, usually the language of families is common. I already said that every node can have at most 2 children, right? Then we can talk about uncles, grandparent. Every node has only one parent, right? So what is the parent of 0, 0, 1? 0, 0. Then grandparents. So this condition actually says that we are always closed under all our ancestors. Okay, so that's a tree. Okay, let's proceed. Now the problem that we are going to state is if T is an infinite rooted binary tree, then does T have an infinite branch? If T has an infinite, if it is an infinite rooted binary tree, does it have an infinite branch? What do you think? Can it just spread out so much that it will cover infinitely many nodes without having an infinite branch? Infinite branch as in something like this. Yeah, this is a branch. I just keep going down, 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 down. What do you think should happen? Is the answer yes or no? No? Why do you think no?
Oh, sorry. Yeah, you just have an infinite branch.
Why do you think yes? Yes.
Because then you can take a finite union, you can take the union of all the branches, and that will be fine.
That will be finite.
No, that will be countable.
I take a moment to think about this. Yeah, it looks kind of obvious that the answer should be yes. You don't think so?
So it's an infinite rooted tree. It doesn't mean that it can go infinitely down.
It doesn't mean that it can go infinitely down.
How are we defining an infinite rooted binary tree?
Oh, how are we? Oh, the definition is still the same. 0, 1 star. Yeah, you look at this 0, 1 to the power n. So this is a finite sequence, obviously. So countable union of finite sets is countable. So I'm giving you a countably infinite rooted binary tree. So it still fits the bill. Yeah, the definition is valid. I never said T has to be finite. I gave you an example of a finite tree, but that doesn't mean T has to be finite.
But every layer adds to a power of 2 increases, so we can say that if it terminates somewhere.
So suppose n is omega, then for the number of nodes, we can say that the length would be log of omega base 2.
Length would be log of?
Omega base 2.
Omega base 2. Okay, I don't know how to do logarithms with ordinal numbers. What could be the value of log of omega base 2? It should be omega, if at all it exists. And why can't it happen that maybe there is one branch with length 1, then another branch with length 2, then another branch with length 3, and so on and so forth? Why does it have to be the case that there is only one branch? There exists a branch which is infinite in length.
So infinitely rooted binary tree means that it extends infinitely.
It has infinitely many nodes. I am not saying that it extends infinitely. I don't even know what that means. Any other ideas?
2 raised to the power n is infinite, then n has to be infinite.
Who said that 2 raised to power n has to be chosen?
That would be the number of nodes.
Maximum
If
number.
n is the length of the.
If n is the length of this, then what is the maximum number of nodes?
1 plus 2 plus 2 square plus g.
Right, okay, sum of some geometric series. That will be a finite number. We are going to use that, but why am I asking it now? Because this is an application of the completeness theorem. We are going to prove this statement using logic. But it's not directly an application of the completeness theorem. We have to go via the compactness theorem. So on the next slide, I'm going to, so this is called, the answer is yes. And this is called Konig's lemma. Okay, and we are going to prove Konig's lemma. You have heard the name of Konig? CSB theorem's proof was by Julius Konig. This is a different Konig if I understand correctly. So Konig's lemma, and the proof is via compactness. Okay, so I'm going to state the compactness theorem now. So compactness theorem can be described as a purely semantic version of the completeness theorem. By the way, when people usually refer to the completeness theorem, then they refer to both of them simultaneously, completeness and soundness. Yeah, because well, if your system is not sound, then you might as well throw it in the bin. Okay, so compactness theorem, what does it state? So if S is a subset of, maybe instead of if, let me write suppose S is a subset of SL, then S is satisfiable if and only if S is finitely satisfiable. Okay, what is meaning of finitely satisfiable? This means that each finite subset of S is satisfiable. Now, which one do you think is easier to verify? That S is satisfiable, each finite subset is satisfiable. Although there are infinitely many of them, that part is still easy to do. And whenever you see the word finite, what comes to your mind in the context of propositional logic? We have seen something that is always, finite. Length of a proof is finite, okay, and as a consequence of that, what did we prove? The finite character lemma. So every proof, if there is a proof of T from an infinite set, then there is a proof of T from a finite subset. And this is simply the analog of that. So let us prove it very quickly. Yeah. So one side I don't need to prove. If S is satisfiable and V is a model of S, then V is a model of every finite subset. So I'm not going to write this. Only the converse. Suppose S is unsatisfiable, means contradictory. Then what will happen? If it is not satisfiable, then what do we know from slide 1? Oh. If it is not satisfiable, then it is inconsistent. Then by completeness, version 1, S is inconsistent. Then what can we say? If it is inconsistent, then what is a test for inconsistency? Then for some T belongs to SL, there is a proof of this contradiction by lemma 7. Yet there is a proof of a contradiction from S. Now, by finite character lemma, S prime proves negation T implies T for some finite S prime subset of S. Correct? Then again by lemma 7 is two-way. Yes, so again by lemma 7, S prime is inconsistent, and then what? If it is inconsistent, then finally we use soundness version 1. If it is inconsistent, then it is unsatisfiable. And by soundness version 1, S prime is unsatisfiable, and therefore S prime is a finite subset, so that is insatisfiable. Therefore, what can we conclude? That S is not finitely satisfiable, because one of its finite subsets was not satisfiable. So this is simple compactness theorem. It looks very simple now that we have proved completeness, but they are equivalent. Yeah? And compactness theorem is an extremely powerful tool in logic. Okay, model theory is really model theory is the study of only semantics, and compactness theorem is the key to studying model theory. So we have just proved compactness theorem, and now we are ready to attack our problem, which is Konig's lemma. So let's state the Konig's lemma. So if T is an infinite rooted binary tree, then T has an infinite branch. Okay, we have to do quite a few things over here. So first of all, let us define Tn to be the set of all those nodes in T whose length is n. Yeah, length you understand? It's a finite string of symbols, finite word of symbols. So 0, 1, 0 has length 3. Yeah, so Tn is this. Now the observation that you all made some time ago is that clearly Tn is finite. But another observation that we can make, and non-empty. Why is it non-empty? See, if you chop down the tree at level n, then there cannot be anything below that level. Because whatever is below that level, it will have a parent, it will have a prefix at level n. So therefore, if this doesn't exist, then nothing below it exists, and therefore we can conclude that the tree is finite. So obviously we are not given that T is finite, we are given T is infinite. So therefore Tn is non-empty for each n less than omega. N is arbitrary. Okay. Now we are supposed to find a single branch. What property will that branch satisfy? If you look at this particular tree, and suppose this is my red branch, yeah? Then notice this particular level. What happens at this level? How many nodes are actually present in that level and which intersect the branch? Exactly one. Yeah, we have to express that there is exactly one node at each level. And moreover, observe that since 1 0 0 is there in that branch, its parent is also there, right? Its parent is also there. So whenever sigma is less equal tau and tau belongs to the branch, then sigma must belong to the branch. We are going to encode all these things in terms of some propositional formulas. Yeah, that's our goal. If we do that, then we can use compactness theorem. We will write down an infinite set of formulas, and we want to show that it is satisfiable, okay, and it is satisfiable if and only if it is finitely satisfiable. So we'll verify finite satisfiability. So that's our way of operation. Okay, so define L. What is L? Our language. L to be P sub sigma such that sigma belongs to D. So we have taken a set of propositional variables, one variable for each node of the tree. So this is a countable language. Okay. So consider the following set of formulas. Okay. So I'm going to call it S. Okay. So here I'm going to say Tn for n in n less than omega, union un n less than omega, union, I'm just going to write this, S sigma tau, where tau is less equal sigma, and tau and sigma are in the tree. So I'm going to take three different kinds of formulas. So the Tn, yeah, where Tn is the formula a big disjunction, but it is still finite, of sigma in Tn, that P sigma. What does this say? Oh, I mean the intended meaning is that, I mean whenever we will define a valuation, yeah, and the intended meaning of this valuation, we want to show that this set S is satisfiable. We'll prove that it is finitely satisfiable, but if it is satisfiable, then there is a valuation. So what is the intended meaning? Maybe I should write that. Yeah, the intended meaning so V of a formula T is true if and only if T, I mean V of maybe I should say V of a particular P sigma is true if and only if sigma lies in the infinite branch. the chosen infinite branch. That's our intended meaning. So we'll make a particular variable true if and only if this happens. So with that idea, can you understand what this is trying to say? Either P sigma 1 is true or P sigma 2 is true or P sigma k is true. One of them has to be true. So for everything in Tn, Tn is the nth level. So that means the branch must pass through level n. Right? So the infinite branch must pass through level n. That is Tn. Then Un is the formula. What should it say? Exactly 1. So I should say that if sigma 1 and sigma 2 are both in level 2, then simultaneously P sigma 1 and P sigma 2 should not be true. And I should take a big conjunction. Disjunction. No. So this formula, P sigma 1 and P sigma 2, that is not simultaneously true. So therefore this conjunction is always going to be false. Yeah, and therefore what should I say?
I want it
Conjunction.
false for every level. Yeah, so it should be conjunction.
We want false to be?
We want this to be false for every level, right?
Yes.
So we need a conjunction there.
Here?
Yes.
Yeah, and sigma. We want the formula to be true. Think about it. Yeah, I mean that is where construction of these things is where your propositional logic knowledge comes into picture. So think about it properly. Sigma 1, we want some kind of conjunction or disjunction. And what do we want to say? That if sigma 1, sigma 2 belong to Tn and sigma 1 is not equal to sigma 2, yeah, that's our index set. Yeah, we'll always choose distinct pairs. But what exactly do we want? We want some formula to be true. So which formula should be true? Did you understand the first one? One of them should be true. Now exactly one should be true. Tell me. There is another problem in the tutorial. Yeah, that has similar flavor. You just have to construct these formulas and then you are done. The rest of the proof is quite standard. Do you want P sigma 1 and P sigma 2 to be true simultaneous? No. So maybe we are not writing the correct thing. Should we simply write for each sigma 1 and sigma 2, P sigma 1 and P sigma 2 is false? Or NAND or NOR, whatever you can think of. Come up with a formula.
So this is correct.
This is correct? Is everybody convinced?
Both of them are not simultaneously true, then the conjunction will be false always, and
Conjunction will be false, so the negation will be true.
and their conjunction will be true.
Their conjunction will be true. Correct? Is everybody convinced? So, the infinite branch must pass through at most one node at level n. That is the intended meaning for this particular statement. And finally, what is S sigma tau? S sigma tau is very simple to state. It just says, I'm just going to write it here. That is P, whenever a descendant is in the branch, then its predecessor is in the branch. So now we know tau is less equal sigma. So what should I write? P sigma implies P tau. Okay. Okay, so this is the formula, and I already gave you the interpretation. Now we need to show that we need that S is satisfiable by compactness. It is sufficient to show that S is finitely satisfiable. Now you can see why finite satisfiability is useful over here. S is infinite. Yes, because S contains this, both of them are indexed by natural numbers. And also T is infinite, so the set of related pairs in T, pair of pairs of nodes, that is also infinite. But what will happen if you choose a finite subset? How many of such formulas Tn and Un can it contain? Only finitely many. So let S0 be a finite subset of S. Then let us choose and fix maximum n such that either Tn belongs to S0 or Un belongs to S0. Okay, so there will be a maximum number, of course, because it's finite. Then S0 is contained inside the set Tn n less equal n union Un n less equal n union, the last part I am going to keep as it is. S, what did we call it? S sigma comma tau. Tau less equals sigma, tau sigma is in T. So S0 is contained inside this. We are going to show that the right hand side is satisfiable. And therefore the left hand side, because it's contained, it will be satisfiable. And since S0 is arbitrary, S will be finitely satisfiable. Okay. Okay, so how do we show? We show that RHS is satisfiable. Now RHS is not finite at the moment, but it is still manageable. Okay, so now how exactly are we going to do that? Look at the tree. Yeah, so suppose I have chosen this level 2. My capital N is level 2. Yeah, then what do I know about level 2? From next page, level 2 is finite and non-empty. If it is non-empty, then how can I define a valuation. If it is non-empty, then I can say I'm going to use yellow color. I'm going to say this particular variable is true, then all its predecessors are true and everything else is false. If I say this, then what will happen? You look at this. Up to level 2, Tn will be true because there will be at least one element intersecting that branch. Then Un will be true because there will be at most one element which intersects that branch, and this will be true. Why will this be true? Because we only chose the predecessors of a fixed element. So either P sigma will be false, or whenever P sigma is true, then all its predecessors are true. We have ensured of that for only those finitely many nodes. So that's all. So since Tn is non-empty, choose some node. Yeah, I mean, let me call that node choose sigma naught from Tn. Okay. Define a valuation V from L. Right now we are not going to do it for SL. We'll just do it for L. L to true false by sending any sigma to true if sigma is less equal sigma naught and false, I mean not false, we use a different symbol otherwise. Now this is an arbitrary function. I will leave this as an exercise, so please verify. V is a model of the left hand side. Yeah, I mean this is S1. V models S1 so that V models S0. Since S is S0 is arbitrary, S0, S is satisfiable. S is finitely satisfiable. I already gave you how to do it. I already told you how to do it, but you should just verify. Any questions? So, can you see that, I mean, a totally unrelated seeming problem can be solved using logic, because logic is the language of mathematics. Yeah, we could guarantee existence of an infinite branch in an infinite binary rooted tree. Yeah, that's the beauty of compactness theorem, and hence the branch of logic which is called the model theory. Model theory is only study of semantics and its applications to algebra and other areas of mathematics. There is one very small thing that I want to talk about, and that is decidability. When do we say, okay, so I want to talk about decidability of PL. PL stands for propositional logic. Okay, so the question is, given a finite S and T in SL, does there exist a decision procedure or algorithm to check if T is a logical consequence of T or T is a deducible from T. Yeah, I can use any turnstile symbol. Does there exist a decision procedure like that? What is the meaning of a decision procedure? It says that some algorithm which will take S as an input and T as an input, and it will tell me after a finite amount of time, that finite could be millions of years, but after a finite amount of time it should be able to tell me whether T is a logical consequence of S or not, both. Yeah, it should be able to decide it completely. Does there exist some similar procedure? Procedure like that? You already know the answer. You just don't know that you know the answer. Yes? No, not using completeness. We don't need to do anything. I have stated the simpler version actually. I should state this problem instead. And then by using completeness, we just have to check logical consequence. And how do we check logical consequence? By using valuations. How many valuations will be relevant here?
2 per
2 to the power yes something. Cardinality of?
the finite character, like whatever you're using in the S.
See, S is finite and T is a single formula. So S union singleton T is a finite set. So therefore, the number of propositional variables which appear in S and T are finitely many. Call that number n. You check for all those 2 to the power n valuations. Whenever a valuation, this is P1, P2, Pn, then you will have S1, S2, Sk, all the elements of S, and then finally you will have a column for T. Okay? So, whenever in a row all the S1, S2, Sk are true, you just have to verify that T is true. And this can be done. Yeah? And with 100% confidence you can say it can take exponential amount of time, but it can be done. So the decision problem has a solution. So therefore we say that using truth tables, yeah, it's not efficient. Yeah, it's not efficient because exponential in the number of variables, number of propositional variables appearing in S union T, but it can be done. So therefore we say that PL is decidable. Another way to state that is that it is also recursive set. The set of tautologies is a recursive set, which means you can list all the tautologies and also list simultaneously all the statements, all the formulas which are not tautologies. You can list the set as well as list the complement in a recursive manner. At this point, I will just guide you to one particular video. Yeah, and that video is by spanning tree. So please watch video by spanning tree on halting problem. Okay, And this is not an optional thing. Yeah, everybody should watch this. Okay, let's stop